length of, say it's length 2, and if I cut that string in half to length 1, I get the same pitch higher, called an octave, right? So here's, let's take a look at the picture. I get a figure 8. And there is my octave. I mean, it's interesting to think about, I don't know if you know music at all, but we call an octave an 8 VA, right? And the first time I saw an 8 come out when I was playing an octave, I was like, what? And of course, do, re, mi, fa, sol, la, ti, do, it's the 8th note of the scale, right? But it turns out it's not as cool as that. It's really just lowest common denominators is what's happening. So I've got a 1/2 ratio, right? And so 1 times 2 is giving me the 2 pedals, right? So just to let you see, if I cut the string, if I cut a string of length 3 into length 2, right? I cut one third of it off, I get a 5th, and this is my 6-sided star here, or 6-sided flower. And so that's my 2/3. So what's making this thing give me a nice picture is, of course, right, that the 2 and the 3 will eventually meet up again, just like LCDs, right, or times tables. If I play something that's dissonant, right, something, it's having a hard time settling to a nice looking place, right? But if I play something that sounds better together, right, I get a little bit more of a, right? And it's just like rational and irrational numbers kind of idea. So let's take a look at what happens with the octave, right? Let's take a look at, Harold, do you need to come through here? So when I do an octave, and so all of this was actually discovered, or at least written down first by Pythagoras. Pythagoras was hearing someone, doing metal work, and they would be hitting hammers, right, of different weights. And when one weight was twice the weight of another one, you got that octave harmony, right? And so same thing here that I'm showing you with the length of the strings. So what I have is I have 2 points moving around a circle now. So since I'm playing 2 notes on my guitar, right, there's 2 points moving around a circle, so 2, and one of them is moving twice as fast as the other, right? Can you see that? So that's the same as my string length of 1 and the string length of 2, right? And so what's going to happen is there's an interaction between those 2 points on the circle. What it's going to do with the single point is a circle, the other single point is a circle but twice as fast, and then together they're going to cause that little interaction and give me that shape for the octave. So here's me playing the octave. Integer string lengths will give nice shapes, right? Nice harmonies. And so this is one of the things that Pythagoras was always talking about. That, right, if you're always using these whole numbers, you're going to be able to explain a lot of the things in the universe. So there's my octave, a figure 8. Let's watch that one again up here. All right, so there's a little slight difference in what's going on right here. I've got a decay factor happening, right? My note's not going to last forever. If my pedal didn't fail me, it gave me a sustained. It would just keep the note going strong. But so this one, right? No loss of sound quality at all. That's why it's this perfect picture. So let's take a look again at the 5th, because we're going to look at that on Sketchpad in a second. So here's my 5th. I've got a string length of 3 and a string length of 2. And then I don't know if you can see the 2/3. Can you see the 6 pedals? It's a little bit hard to count them. I wish if I could freeze it, you could see it. I think I can get myself to see the 6, right around there. There's 6. There's an easy 6 there. All right, so let's take a look at what's happening here on Sketchpad. This is a perfect fit install. So when I play my perfect fit, I've got one sine wave of, right, sine 2x and one sine 3x. So, right, one is moving 1.5 times fast as the other one, right? And so here is my picture of my perfect fit. Sorry. Okay, here we go. Play the perfect fit. So here's our perfect fit happening. Now there's something called a harmonograph, and you can find them on YouTube a lot. So what actually is happening is called a rotary harmonograph. What's going on with my speaker is actually creating a three-dimensional object, right? It's moving in and out and around, right? And I'm just capturing some flat image of it here on the ceiling. And there's my harmony of a fifth. So as soon as I throw in a little extra sound, it's gonna, right, there's the vibration of the speaker. Right? So, let's take a listen to another piece of music here. So one of the things I want to do is, if you have it's a regular like headphone jack on your phone or anything you're listening to music on, give you an opportunity to play something of your own in a few minutes. So we were playing a little bit of Indian music before, and I just loved the way the tabla looked. So I want you to see some of that. So it's here in Nawala. There she is. My speakers really picking up the low tones. The high tones are coming out of the tweeter. So this is just resonance on that bigger speaker. As soon as the tabla kicks in. Monica, is this what we were playing before?
Mm-hmm. Yeah.
I'm looking at that and I can hear when they're playing certain harmonies. It's fascinating. So, so what I'd like to do is I want to see if there's any questions right now. Do you have any questions for me? Are you, yes, question?
Okay, so is there any connection between cosine? Because so far we only showed the sine function.
So as you know, it's a point moving around a circle, right?
Yes.
Okay, so there's an x coordinate and a y coordinate of what's going on. And so if you look at my perpendiculars of my 2 points, that's how I'm getting the interference of those two string links, right? I'm using a perpendicular for 1 point, right? And well, perpendicular to this line and horizontal to this line to find that intersection, right? And that's that path that's being traced on the speaker. So cosine is always just an x coordinate wise. And so if you looked at my speaker, you would see I have my mirror on a 45. I was doing it before last night. I was practicing and I had it on the y-axis, and my circles were all flat. I could only see a line going back and forth, right? So I wasn't getting that x interference from it. So yes, if there's a sine involved, there's a cosine involved.
My other question is,
Yes.
is it possible to create music with just math equations alone?
Yes, exactly what can happen. You can just tell oscilloscope what harmonies, right, to play. And you can just get the visual of it only. Yes?
If you had a melody with a lot of consonants in it, like
Yes.
Mary Had a Little Lamb, what would that look like?
Well, so wait, when you say consonants, you mean?
The melody line, no harmony, but the
Yeah,
melody
all
line
circles.
has consonants.
If I only play single notes, it's all circles.
Yeah, but consonants, so that you'd get easy shapes.
Sure. So I just want, no, I don't need that one point. I just need to make sure.
Or maybe just play notes consonant, no seconds. Or,
Yes, so a
yeah.
single note is going to give me a circle every time. Here it is. Now, so if I just hit a string, there's, if you know, there's harmonies, the harmonics are happening. So I'll often, even if I just hit a single note, I will show. So that is a circle. It's not doubled up on itself. It's just twisted a little bit, right? So, but if I just play single notes, right, like a scale, I'm just going to get single circles. As soon as I put those harmonies in, and then as soon as I put a third harmony, I get even more interference. Be nice if it was in tune, but you get the idea. Other questions? Yes?
Typically in the United States, all music is kind of based on 4/4 time. So if you were to apply this principle to actual real-time sheet music, would your x-axis kind of be your reference of like T? Would these like shapes move along? Like what would it look like if it was actually done real time? If it was moving as a function of time with the x-axis being?
I mean, you know, so we are, as I'm playing, right? I mean, it is changing. As if I'm reading music, right? If I'm reading music right now. So, I mean, it is playing. I don't know if you're talking about something moving across.
Like how you read sheet music, how would it look? Would it be just shapes moving?
Yes, but the shapes wouldn't be moving. The shapes are stationary. So I actually would envision one piece of music just my one picture, and as the music is changing, that one shape is changing. So you'll see different harmonies morph into other ones, right? So you'll see a fifth morph into an octave, right? Or into a third. So as the music progresses, one shape just kind of turns right into another one. Yes?
So basically, like, if it's just one note, it's also always going to be the same, but there's other factors that affect the shape, such as like, if you're playing on an instrument, there's a vibration that will slowly fade.
Exactly, yeah, exactly, and that's why, right, so as soon as I get any kind of distortion, so there's my single note, right? But what happens is, as that thing, so now right, the amplitude is dying, so the circle's small, getting smaller, right? Why is it not spinning perfectly like this, right, is because there's a little bit of distortion in it, right? So there's a pretty good circle. So there's some distortion or me bending the note a little bit, right? So there's me bending a note. Cool. What else? Anything? Yes?
So do all the single notes keep the same circle?
Yeah, not the same. So you'll see often, right, when the music was playing, you'd see really big, right? So my speaker is going to react to the frequency, that speed, right? And so if I've got a really low note, right, that's really going to give me that big circle at the end, right? And so if you'll see the higher notes, so let's see if I can play something else here. So those higher notes are it's really that tight circle.
So pitch, as it relates to the X and Y axis, if it's lower, it's gonna be wider along the X axis. If it's higher, it's gonna be higher along the Y axis.
When I get when the frequency is faster, right? So that's right. When that frequency is that big note, it's just stretching out my speaker like that. So all single notes are that circle, right? And so if I had mirrors everywhere on here, right, and I could just show the entire speaker, every single note would sound the same. But because I'm focused on one particular point on my speaker, right, the high notes look different than the low notes, that type of thing.
Could you show us again?
Yes, show what again?
High and low notes.
Sure.
Big song.
Yeah, I was gonna put one on the song there, but, so again, the real size is the amplitude, but if I'm just playing this is my lowest note on my guitar, okay? And here's the octave higher. You can see, I mean, so it's the same, it's another circle, right? My lower one is just, I'm getting a little, there we go. So it's sideways, but it's a circle. So there's a lower note, right? Here's a higher note. It's just how that particular point on the speaker is happening. The amplitude comes from my volume. How big this thing is from my volume. If I turn it up, I'm gonna get a bigger circle, right? So, but again, those notes are moving at different speeds around the circle, which is gonna put my speaker in a different position, right? And that's why the circles look different sizes. Okay, one more song, and then I'd like to, if anybody would like to volunteer one of their pieces of music. Is there any lights for me? A little bit of light?
Yeah. Turn on the light. I'd kind of like to see what this crazy death whistle looks like.
We know what it sounds like.
Yeah. Sort of like it.